All right. Before I get into material today, I want to show you something on D2L. Okay, so if you go into physics, if you look at the announcements, it says stuff about lectures and assignments for Monday and Wednesday classes, and then for Tuesday and Thursday classes. Okay, this D2L site is for a class that meets Mondays and Wednesdays and a class that meets Tuesdays and Thursdays. So it's a little confusing, I know. But you only want to pay attention to the stuff on Tuesdays and Thursdays. You guys are sections 13 and 14, okay? So, so this assignment that I gave yesterday for the Wednesday class, that's not for you, okay? After class today, I'll put up something that says assignment for Thursday 8/24, okay? Everybody with me on that? And that's true throughout this whole site. So if you look at videos, there's a video you can watch about when I was discussing the syllabus and stuff last time on Tuesday. Then this is the lecture from yesterday for the Wednesday class. That's, it's the same material. It's very similar to what we're going to get to today. But you can just ignore all of the stuff that says Monday and Wednesday, sections 11 and 12, and just look at the stuff that says Tuesday, Thursday, sections 13 and 14. Okay? Also, I can show you while we're here. Today I'm going to give you the first assignment, and it won't be due until Tuesday. But when you do the assignment, you can go to Assessments, Assignments. And again, the only one that's posted so far is the assignment I gave to the Monday, Wednesday class. But there'll be something here that says Assign Thursday 8/24. And that's where you're going to put your photo files or your PDFs. Okay? Any questions about that? In retrospect, I probably should have just split this up into two D2L sites, but they make you do it like 6 months in advance, and I didn't think of it. So anyways, we'll get through it. Also, everybody has had their first lab. So you know where the lab is and everything. A lot of people were late. It's okay. It's, new thing. But starting next week, I'm going to start every lab with about a 20-minute discussion of what you are going to be doing. And if you miss that, it's very hard to do the lab, okay? So starting next week, you have to be there on time. If you're 15 minutes late to lab or more, you can't get credit for that lab, okay? So remember to be there on time. If you're a couple minutes late, few minutes late, that's one thing. 15 minutes is the cutoff for me, okay? All right. So today, for the first time, we're going to get into material in this class. And the first thing we have to talk about is units, unit conversions, scientific notation. And then hopefully today we'll get to unit prefixes like milligrams, kilograms, that kind of stuff. Okay, so first let's talk about units. So physics equations are relationships between measurements, things you can measure. And every measurement, every physics measurement, let's say, has units of some kind. So like if you're measuring the length of something, and you measure that the length is 3.5, the question is that 3.5 miles, 3.5 inches? You know, that's a big difference. In this class, every unit that we're going to use is a combination of 3 basic unit types. So everything is a combination of 3 basic unit types. Those are length, and length can be, you know, inches, feet, meters, miles, so on. Time, and that can be seconds, minutes, hours, years, whatever. And then mass. And mass can be grams, kilograms. It's interesting that in British imperial units, like feet and pounds and stuff like that, we don't tend to use units, measurements of mass. You might think that pounds and kilograms are both units of mass, but pound is really a measure of force. The British measure of mass is actually called slugs. You've probably never even heard of that. I've never used it in a calculation, but in SI units, which is what we're going to use, the measure of mass is kilograms. Okay, so for almost everything, we're going to use SI units. You can think of SI as standing for Standard International. It really stands for some French version of that I'm not going to try to pronounce. But the SI units are meters for length, seconds for time, and kilograms for mass. So those are the most common units we're going to use. Okay. And as far as combining these units, here are some, you know, we're going to see units of meters per second for velocity and speed. We're going to see units of meters per second squared for acceleration. We're going to see units of kilogram meters per second squared for force. Okay. And so you can see that all of these, even though they're measuring their own things, they're made up of, you know, multiplying and dividing these 3 basic unit types. Okay? So one thing that we're going to often want to do is convert from one unit of a certain type to a different unit of the same type. So an example of this would be how many inches are there in 3.5 feet? Okay. To do this conversion, feet and inches have to be the same type of measurement. They are. They're both measures of length. You can't convert from feet to seconds, you know. So there's sort of a general approach for going about this. So first of all, there's always a conversion between any two units of the same type. There's always a conversion between any two units of the same type. So for this example that I gave here, we know that 1 foot is equal to 12 inches. Okay? For each conversion, you can come up with 2 conversion factors. So the conversion, that equation that I gave there, gives 2 conversion factors, and you get those by dividing one by the other one. Anything you divide by itself gives you the number 1. You know, if you divide 4 by 4, you get 1. Just like that, if you divide 1 foot by 12 inches, you're dividing something by itself, so you get 1. And so you can multiply these fractions to anything without changing the value. That's sort of the property that 1 has, you know. You can multiply 1,000,000 times 1 and you still get 1,000,000. So this conversion gives 2 conversion factors. And those are 1 foot over 12 inches, which is equal to 1. And that's also equal to 12 inches over 1 foot. You're just dividing it by itself, just in a different form. And so then what you do is multiply your original value by the conversion factor that cancels the unwanted units. By the conversion factor that cancels the unwanted units. Okay, so let's look at the example we're working on and think about what the unwanted units are. We're trying to figure out how many inches in 3.5 feet. So our original value is 3.5 feet, okay? And the unwanted units are feet because we want to put it into units of inches, okay? So we're going to start with 3.5 feet. And in order to make the fractions clear, I'm going to think of this as 3.5 feet over 1. Okay? And now we're going to multiply this by either 1 foot over 12 inches or 12 inches over 1 foot. In order to cancel the feet, do we want the feet on the top or the bottom of what we multiply to? Bottom. So we're going to multiply this by 12 inches over 1 foot. And then you can see that, well, I didn't say this yet, but you always, like the mathematical rules for units are exactly the same as if those units were algebraic variables. Think of that feet as if it was the variable x, okay? So just like if that was x, you know, those x's would cancel. Here, this feet on the top cancels this feet on the bottom, okay? And what you're left with for units is just inches. So now we know that if we multiply these fractions together, we're going to get the value we want. And so you get 3.5 times 12 is 42 inches. Okay? If you accidentally multiplied by 1 foot over 12 inches, you'd have inches in the denominator of this second fraction. That doesn't cancel with the feet. And so you'd get these crazy units of feet times feet over inches, okay? And that's not what you want. It's fine. I mean, you could think of that as a unit of length, but no one ever wants that unit of length, you know? Anybody have any questions about that first example? Okay. So this can get more complicated if the units that you're converting are like these combinations, you know? So let's do an example now. Where we go, so let's say we want to express $38,640 yards per minute squared in units of meters per second squared. And the conversions that we want to use here are, we want to use that 1 yard is equal to 3 feet. 1 meter is equal to 3.281 feet. And 1 minute is equal to 60 seconds. Okay, so the way we're going to do this is we're going to multiply this original value of 38,640 yards divided by minutes squared by a conversion factor that goes from yards to feet. That's still not the unit of length that we want, so then we're going to multiply by another one that goes from feet to meters. Then minutes squared, we're going to think of as minutes times minutes. That's the definition of squared. So then we're going to do one conversion factor that changes one of those 2 minutes to seconds. And then we'll do it again to convert the other minutes to seconds. Okay? By the way, I'm going to use this notation just to save a few pen strokes, where I'm going to write one big fraction bar, and instead of parentheses, I'm just going to use vertical lines. But all that means is that's just the end of the parentheses. It just sort of saves a couple seconds. And so this conversion here would have 12 inches on top, 1 foot on the bottom. And this means the same thing as this. Okay. Okay, so I'm going to start with a big fraction bar. And now we have to think about what's in the numerator and what's in the denominator of the starting value. So we have 38,640 yards divided by, instead of minutes squared, I'm going to write this as minutes times minutes. And now we're going to multiply by a conversion factor that takes yards to feet. The yards here are in the numerator. So we want the conversion factor that has yards in the denominator, so they cancel. So 1 yard is equal to 3 feet. And as I go, I'm going to keep track of the cancellations. So the yards now cancel, and the units of length that we have are feet, so that's good. We're getting there. And now I want to go from feet to meters. Here I have feet in the numerator. So my conversion factor, I want feet in the denominator. So we have 3.281 feet. And 1 meter in the numerator. And then those cancel. So now the only units we have left of length are meters. So that's perfect. Now we have to deal with the minutes and convert those to seconds. Okay, well, this is the first time I've done one like this, but now these units are in the denominator in the starting value. So we want a conversion factor that has minutes in the numerator, okay, to make it cancel. So now I'm going to write 1 minute over 60 seconds. And that cancels the first one of these. So one of those 2 minutes has been converted to seconds, but now we have to do it again, okay, to get rid of this other one. Right now we have 1 second on the bottom and 1 minute on the bottom. So we'll go one more time, 1 minute over 60 seconds. So that one cancels that one. And what we're left with is units of length of meters, units of time of seconds squared. And so now we know if we just multiply and divide out all these numbers, we'll get the right answer. And if you multiply this out, you get 9.81 meters per second squared. Anybody who's taken physics before know what that value is? That's something that's going to come up all the time in this class, 9.81 meters per second squared.
Isn't gravity?
Yeah, that's the acceleration of gravity for something that's in free fall or projectile motion, if there's not a lot of air resistance. So any object that you drop, if it's not too affected by air resistance, is going to accelerate down with that value. Yep. So we'll see that all the time. That's going to come up in a lot of different areas. Anybody have any questions about that process? Okay, let's go through a calculation. I'm going to write this up here, and I'm going to give you a few minutes to work on it. And feel free to work together or ask me questions if you get stuck. But I'm going to give you a few minutes to do it, then I'll do it, and you can sort of see if there's a point where you got confused, something went wrong, or you got stuck, okay? Okay, so let's convert 61 miles per hour to meters per second. And we're going to use the conversions. 1 mile is 1609.344 meters. And 1 hour is 60 minutes. And 1 minute is 60 seconds. So take a few minutes and see if you can work through this. You can compare answers with each other as you go. Ask me if you get stuck, and then I'll go through it once I've given you some time. Okay. So we'll start with, I guess I'll start with the fraction bar. In the numerator, we have 61 miles. In the denominator, we have hours. I'm first going to go from miles to meters. We want the miles in the denominator to cancel this one. So 1 mile is equal to 1609.344 meters. And you can see now those cancel, and the only unit of length that we have left is meters. And now we'll go from hours to minutes. These hours are in the denominator, so in our conversion, we want hours in the numerator. So we'll go 1 hour over 60 minutes. And this cancels. And we're almost there. Now we have, if we multiplied and divided out all these numbers, we'd have units of meters per minute. So now we have to convert the minutes to seconds. In our conversion factor, we want minutes in the numerator. So we'll go 1 minute over 60 seconds. And the minutes cancel. And what we're left with is units of meters divided by seconds. So that's what we want. And if you do this calculation, you get 27.26 meters per second. I think that's right. Yes. Anybody have any questions about that? So the real benefit, like I'm going to do this a lot, give you a problem to work on, give you some time, and then I'll go through it. And the benefit is, well, if you do it right, you can see that you did it right. But really, the big improvements you can make are when you make a mistake or you get stuck, you can see exactly where the problem was, okay? So look back at that if you didn't get that answer. One other thing, I haven't said this yet. The people who've taken chemistry, probably your chemistry teacher, cared a lot about significant figures. I don't care about significant figures, so you don't have to worry about what you round to. You can round to whatever makes sense to you. Maybe if your chemistry teachers didn't care so much, maybe I would care more, but I know that someone else is dealing with it, so I don't have to, you know. So if you want to use significant figure rules, feel free. If you want to round that to 27.3, that's fine with me. I just want to see you do the steps right, okay? Speaking of that, when you turn in assignments and tests and everything, you need to show me the steps of your calculations. I can't really grade anything just based on the answers you give me, okay? So be sure that in everything you turn in, you're showing all the steps of your calculations, okay? All right. So the next thing we have to talk about is scientific notation. And the idea of scientific notation is that any number can be represented as one non-zero digit decimal point, decimal, times 10 to some integer. So for example, 31,460, you could write that as, well, let me actually make that negative. You could write that as negative 3.146 times 10 to the fourth power. And 0.007, let's say 0075. You could write as 7.5 times 10 to the minus third. Okay. Why would you want to do this? Yeah.
3 times to the third, not 10 to the negative third.
This one would be 10 to the negative third because, so anytime the starting number, anytime the absolute value of the starting number is bigger than 1, that exponent will be positive. Anytime the absolute value is smaller than 1, it'll be negative. Yes?
Do you ever use E?
It's fine with me if you do. I do actually use that, but in this class I try not to. But so the one thing you don't want to do though, because it also drives the chemistry people crazy. So you could write this as negative 3.146 E4. Don't write it as negative 3.146 times e to the fourth, okay? Because that's a totally different thing, okay? I use this notation a lot because that's how you enter it into a calculator. But don't do this.
Don't be on test like that?
You can write it like that. It's fine with me. Just don't do it like the one crossed out. Any other questions? All right, so what's the benefit of writing things in scientific notation? There's kind of two benefits. The first one is if you have very big numbers with very big absolute values, they could be positive or negative, or very small absolute values, like way, way smaller than 1. It can be really tedious to write it in standard notation. Like, for example, physicists do calculations with the orbits of planets and stuff. And so you need to use the masses and the radius of the Earth, stuff like that. The mass of the Earth is like 6 times 10 to the 24th power kilograms. So, like, how would you write that, In standard notation, you'd write it as 6 and then 24 zeros. So get to work, 1, 2, 3, so on. And it's very easy to be off by 1 or 2 of those. And if you're off by 1 or 2, that's not a minor error that you've brought into your calculation. If you're off by 1, you've multiplied your answer by 10 or divided your answer by 10. If you're off by 2, you've multiplied or divided your answer by 100, And so that's a big problem. And so it's much easier to write this without errors as 6 times 10 to the 24th than to write 6, 0, 0, 0, 0, 0, takes you 4 minutes to write your answer. The other benefit of scientific notation is, if you remember when you talked about significant figures, there are all these rules. They do kind of make sense, like once you've worked with them a bit, but you probably remember at first hearing all these rules like, what? Like, it's like, okay, do you count zeros? Well, you do count zeros if they're before the decimal, you don't count zeros if they're before the decimal point. But then if there are any zeros after the decimal point, you go back and count all of those other zeros. And now you count the ones, you know what I mean? Like, it's a little confusing. Remember doing that stuff? It's really easy if you're given a value in scientific notation. In scientific notation, the number of significant figures is just all the digits before the times 10 to the whatever. So in this case, if you look at these numbers in scientific notation, we have 1, 2, 3, 4 significant figures on that first one. And on the second one, 1, 2, so we have 2 significant figures. Okay. So there's no like sort of confusing rules to remember. If your numbers are in scientific notation, it's really easy to know how many significant figures you have. Okay, well, to use scientific notation, there are 2 skills you need to have. You need to be able to go from standard notation to scientific notation, and then you need to know how to go back the other direction. Okay, so you need 2 skills. The first one is if you're given a number in standard notation, express it in scientific notation. So I'm going to do this, I'm going to follow through these steps using this example of negative 541.6. Okay, so the first step, A, count the number, we're going to call this number capital N. So count the number of places, we'll call that capital N, that you have to move the decimal point for 1 leading digit. Okay, so in the example that I'm using, we're starting with negative 541.6. To have 1 non-zero digit before the decimal point, we have to move this 1, 2 places. Okay, so this capital N is equal to 2. Then second, if you moved the decimal point to the left, then you're going to multiply your number times 10 to the positive n. And if you moved to the right, you're going to multiply by times 10 to the minus n. Okay. So in the example that I'm using, we move 2 decimal places to the left. So our answer is going to be negative 5.416 times 10 to the positive 2. Instead of remembering left and right, you also can think if your starting number has an absolute value that's bigger than 1, your exponent is going to be positive. And if your starting value has an absolute value less than 1, your exponent is going to be negative. That does the same thing. Okay? Any questions about that? Okay, the second thing you have to be able to do is if you're given a number in scientific notation, you have to be able to write it in standard notation. Or express it in standard notation. Okay, so for this one, I'm going to use the example 6.52 times 10 to the minus 4. Okay, so the first step is n, this number n, is the absolute value of the exponent. So in this example, capital N is equal to 4. And then once you have that, if the exponent is positive, move the decimal point n places to the right. And if the exponent is negative, move the decimal point n places to the left. Okay, so in this example, we know we're going to move the decimal point from its starting position 4 places one way or the other. Our exponent is negative, so we're going to move it to the left. So we're starting with 6, 5, 2. We're starting with the decimal point here. We're going to go 1, 2, 3, 4. Put zeros in all these placeholder positions. And there's your answer. Okay. And again, I don't know, I have it written as you're deciding whether to move it left or right. You also can just think a number with an absolute value smaller than 1 relates to a negative exponent, and a number with an absolute value bigger than 1 relates to a positive exponent. And that does the same thing. Like in this case, you know you're going to move it 4 places, one way or the other. This is a negative exponent, so you know you're going to have something smaller than 1. And that tells you that those zeros are going to go to the left of the number instead of to the right of the number. Anybody have any questions about that? Okay, the easiest way for almost everybody to do scientific notation. This was not necessarily true when I first taught this class 15 years ago, but is to hit enter again on your calculator and it'll pop up. So I don't know. So I don't want to spend a ton of time on this because how do you do it? Your calculator does it, but it's a nice thing to understand. Okay. And then the last thing we need to understand, need to talk about with units and scientific notation is unit prefixes. So the unit prefixes are like, you know, you can have grams, but you can also have milligrams, kilograms. And so that milli or kilo, those are the prefixes I'm talking about. And there are a lot of them. These are the most common ones, the ones that are most useful, but there's a whole bunch. So first is micro. And it's denoted with the Greek letter mu that looks sort of like halfway in between a cursive M and a cursive U. So that's how you can remember that's mu, MU. And the meaning of micro is times 10 to the minus sixth. And then the next one is milli. That's denoted with a lowercase m. And the meaning of that is times 10 to the minus third. The next one is centi. For that one, you use a lowercase c. And that means times 10 to the minus second. Next is kilo. That's a lowercase k. That means times 10 to the positive third. And then the last one is mega. For that one, you use a capital M. All the other ones are lowercase. And that means times 10 to the positive 6. And then there are other ones that, as you know, computers have gotten more powerful and stuff, we use more and more. Giga means times 10 to the 9th. Tera means times 10 to the 12th. This is funny, like gigabytes, like you're very used to the term gigabyte, you know. So you're used to the prefix giga. When I was, I don't know, how old was I? 12. Back to the Future came out. And if you watch that movie, they keep talking about gigawatts. Like people, like nobody used giga for anything. So people hadn't even decided for sure how to pronounce it yet, you know. Now it's just like part of everyday speech. But okay, so with this, kind of like scientific notation, there's sort of two skills that you need to work with these prefixes. You need to know how to go from something with a prefix to something with no prefix, and you need to know how to go from something with no prefix to something with a prefix. And that way you can also go from one prefix to a different prefix by going through the intermediate step of one without, you know. So like if you're trying to convert from kilometers to millimeters, you're going from kilo to milli. The way you do that is you go kilo to meters and then meters to millimeters. Okay. So all you need to convert from anything to anything else is to be able to go from a prefix to none and then from no prefix to a prefix. Okay. So there are two steps for this. Going from a prefix to no prefix and going from no prefix to a prefix. Okay, so the first one to go from a prefix to no prefix. This is the easy one. So all you do in this case is just replace the prefix with its meaning in this list. Okay? So just replace the prefix with its mathematical meaning. So for example, negative 53 kilometers is equal to negative 53. What does kilo mean in the list above?
Times 3.
Yep, so negative 53 times 10 to the third power meters. I just replaced the K with the mathematical meaning. And then that's sort of a funny in between standard notation and scientific notation. So to get that in scientific notation, you would divide that first number by 10, right? And so if you're dividing this by 10, you have to multiply this by 10 in order for it to keep the same meaning. So you'd write this as negative 5.3 times 10 to the fourth meters. So that one's easy. You just do the replacement. The other direction you have to do as if it's a unit conversion. So you have to think of, well, I'm going to get ahead of myself. So the second one is going from no prefix to a prefix. And this one you do as a unit conversion. Okay. So for this one, let's say we want to go from 20 grams to milligrams. Okay, well, for this, first you have to think of a unit conversion between grams and milligrams using the definition of milli. So we know that 1 milligram is equal to 1 times 10 to the minus third grams. And I got that from this list of mathematical meanings. Milli is equal to 10 to the minus third power. And so now we're going to start with 20 grams. We're going to come up with our conversion factor that cancels the grams. So we have 1 times 10 to the minus third grams in the denominator, 1 milligram in the numerator. The grams cancel. And if you remember exponent rules, I'm sure it's a little hazy for a lot of you, but if you divide by 10 to the minus third, that's the same thing as multiplying by 10 to the third. And so this is 20 times 10 to the positive third milligrams. And now to get that in scientific notation, you're dividing the 20 by 10 to make that 2. That means you have to multiply the 10 to the third by 10 to keep that overall number the same. So this is 2.0 times 10 to the fourth milligrams. Any questions about that? Okay, let's do one more problem. I'll write the problem up here and then give you a little time to work on it. Okay, so let's say that we have 15, it looks like micrometers, but you say that as microns. Okay, so a micron is a really small thing. A micron is a millionth of something, so that's a millionth of a meter. And we want to express that in kilometers, okay, in scientific notation. So take a few minutes and see if you can work through that. And like always, feel free to, ask the people next to you, ask me if you get stuck.